start recording maybe.
Yeah. Today we have the third talk by about computation of kappa classes in the moduli spaces of curves. You're welcome.
Thanks very much. So in the first two lectures, we've set ourselves up to now be able to handle the proof of this vanishing relations. I won't give the vanishing relations here again because I'll give them a bit later, but they're polynomials that will vanish. I want to get into the basically we need some external construction, and then we're going to be using our knowledge of cohomological field theories to do something like this. So let me define this space here. So this is the modulized space of stable spin curves, where, well, maybe I'll write it rather than just say it, where we have theta phi is a spin structure. Theta is the isomorphism, giving phi. Phi is the isomorphism, and theta is the square root of the log canonical bundle. So that's a spin structure. That's what we mean by it. It's square root together with that isomorphism. C is a stable twisted curve. Is a stable twisted curve. Another way to say twisted is it's an orbifold curve. And the isotropy subgroup is Z2, where all the labeled points and nodes are orbifold points. The PJ and nodes are orbifold points. With isotropy subgroup Z2. And this is the log canonical bundle or sheaf, and theta. These are either sheaves or locally free invertible sheaves, say, or line bundles, say. The degree of theta is half the degree of the log canonical. So the degree of the canonical is usually 2g minus 2. Maybe I'll write that out. So how about degree of this is equal to the degree of omega c d. This is the log canonical, where I'm taking the I'm allowing simple poles at the points P1 through Pn. So this actually restricts nicely to any nodal curve, because we've already said that at nodes, we naturally allow these simple poles at the Pi. So the log canonical restricted is the log canonical. That's actually important for us. And so what is this degree? Well, the degree of the canonical is 2g minus 2, and the degree of d is n. There's just n points there. So this is 2g minus 2 plus n, and the degree of theta is half that. So this is a possibly a half integer, which is fine, because orbifold line bundles can have half degree. Just think of just divisors, say, and your divisors, usually you count your points. Your degree is just the number or the sum of the coefficients, the integral coefficients of your points. But now the orbifold points count as a half. So divisors, at least maybe you can believe, have possible half degree. And what do I mean divisors? Take some function on your space and ask for, say, the divisor of zeros of that function. It can have half integral values because the orbifold points, perhaps a function vanishes doubly at that orbifold point, or but perhaps it vanishes singlet. In those cases, it's either half or 2 times a half is 1. So that's fine that it is half integral degree. And now we'll take curly E to be the universal spin structure equals the universal spin structure on the universal stable twisted curve. So where's the universal curve live? And this is just this curve that sits over so MGN spin bar, this is a moduli space that every point in that moduli space gives us a spin curve. And so now this total space here has as fibers each of those spin curves. And as usual, as I explained earlier, the n labeled points means that we have these n sections. So I could have put MGN plus 1 spin above there. This is a disconnected space, remember. Oops, I am not up to that yet. Let me get to that, but it's fine. Okay, and then I'm trying to define. Let me just remind us. Maybe I'll write it, and then let me just remind us of something that we did in the preparatory lectures. So E is, you could call it a line bundle. So let me say, I should call it that. This is a line bundle. It's the guy who's the square root of the log canonical when restricted to each fiber. But as it's a line bundle on C. So that's, when I said universal spin structure on C, I was saying, in fact, it's a line bundle on C. And in fact, let me say, it's an invertible sheaf or a line bundle. We're interested in both this language here on C. And so this is the guy that if you were to square it, you will get the relative log canonical sheaf, which we used in the earlier lectures. The relative log canonical is this guy we called omega pi d. And so then we can take a push forward of a sheaf. We're going to take the dual of this sheaf. We can take its push forward sheaf is, again, it will give rise to a virtual, so this is the, will give rise to a virtual bundle. And this is defined over MGN spin. So we've pushed forward the sheaf from C to MGN spin, and it ends up, it's a bundle with fiber given by the first cohomology. So the in general, this would be a virtual bundle given by H0 minus H1, or I'll put a negative sign here, so H1 minus H0, but we in fact have the H0 vanishes in each. So this, in each case, so this uses the fact that the degree of this dual is less than 0. I said the degree is less than 0. Notice this is less than 0, because notice that this is greater than 0. This is 2g minus 2 plus n is greater than 0, hence g minus 1, oops, is greater than 0, sorry. But the negative of that is less than 0. The degree of the dual is the negative of this. So this is less than 0, but even more, I haven't said restricted to C, I've said restricted to any irreducible component. So C prime is an irreducible component. So this is important. So it has negative degree, and if you have a negative degree line bundle, it has no section. So what this has proven is H0 of the theta dual is, what this is saying here is H0 on each curve of theta dual is 0. There's no global holomorphic sections. And so this thing that would normally be a virtual bundle, H0 minus H1, but there's we've got an actual bundle here. And so let me and I'll make a couple of remarks. So the first remark, when dealing with the modular space of spin curves, previous to this, people didn't take the dual. And without taking the dual, then this nice property didn't occur, and there were virtual bundles, and a virtual class had to be constructed to produce a cohomological field theory. What we're going to do with this bundle is we're going to produce a cohomological field theory just like we did for the to get the lambda classes, just taking the bundle E, that's a vector space of a g-dimensional vector space of holomorphic differentials. So that bundle E is also the push forward, the bundle E over the, oh, I've given it nearly the same name, haven't I? Let me change my terminology, and I hope that I keep it changed. So let me give this the name. So is theta going to look too much? How about a square theta? Yeah. So so this bundle was, it looks a bit like the E, but now an extra line in it. And this is a bundle of, well, I'll tell us the rank in the moment, but I'm trying to give the analog with the Hodge bundle. So the Hodge bundle was a push forward of the log canonical sheaf. So the log canonical on this universal curve, sure, we're over mgn bar, but mgn bar is similar to spin, mgn spin bar. And we took the what we'd call omega pi, where this map we're calling pi, say. And we took this omega pi, twisted it by d, and we took the push forward of that sheaf. And we noticed that the push forward of that sheaf has the fibers of this given by the global holomorphic sections. What I didn't say is actually the push forward should have had some H1. And in fact, there is some H1, but it's exactly a copy of C, and it gives a trivial bundle. And so it's, in fact, part of the push. So in that case, there's a virtual bundle for the Hodge class, for the Hodge bundle, except it's an actual bundle minus an actual bundle. In general, a virtual bundle won't be the difference of two actual. So in this case, we get a bundle without that little blah-de-blah about the trivial line bundle. So this is very much like it. So this is the type we're going to be basically mimicking what one does for the Hodge bundle. And the Hodge bundle was used to produce these lambda classes and the m degree m churn characters classes. And so this is going to be used to produce. So what we get is that the rank of EGN is equal to 2g minus 2 plus a half n plus, remember, there's, no, I can't say remember. I'm just doing things out of order. So let me, I'm so used to some other software where I can circle this and just move it elsewhere on the page, but I don't think I can move this elsewhere on the page. Okay, I need to introduce this notion of sigma. So since theta is a line bundle over an orbifold, what does that mean to be a line bundle? This is the square root of the log canonical. What does this mean to be a line bundle over an orbifold? Well, we've got this orbifold point, and upstairs we have this double cover. That's what we mean by an orbifold point. So locally we have this double cover here, and the line bundle over the base. So I'm going to put a 2 bracket here because this is an orbifold point. So we're used to in Riemann services saying, oh, this is a map Z goes to Z squared just from a disk to a disk, and we ignore the orbifold structure, but there really is an orbifold structure here. So this is the map Z goes to Z squared, and the guy downstairs has naturally an orbifold structure, where this point here, we usually make it a whole point, but in fact it's half a point. And I'll discuss what that means later. Given an orbifold, we can look at the underlying coarse space, which goes back to that viewpoint where this is a whole point. But here it's a half point. And what is a line bundle? Well, a line bundle is an equivariant line bundle upstairs. So upstairs, of course, there's lots of different patches downstairs, right? I've just taken a little patch. And basically a bundle on this orbifold guy is just like a usual bundle everywhere where you don't have an interesting point. But when you have a point with non-trivial isotropy, then I'm going to take this cover here downstairs where one of the open sets has this point in it. And then what I do is, as usual, upstairs, there'll be two sets for the guy downstairs, but I just have locally a bundle. I can describe it just locally. And so then locally around this point, it's an equivariant bundle. Equivariant meaning that there's a Z2 action on the fibers. So this is unusual that you would have this point and you would have a Z2 action that lifts to the bundle. Usually a Z2 action might pull the bundle back, but you can't actually act on the fibers. So anyway, Z2 equivariant. And in particular, so it's Z2 equivariant in a neighborhood of a point. In fact, a point with non-trivial isotropy, but if I go to a point with trivial isotropy, then it just has, well, it doesn't have two disks upstairs. We only use this local double cover locally. But if you were to take two disks, Z2 equivariant, then we'll just be as usual as you're working downstairs. But in particular, over a point, this Z2 action over the fixed point here, this Z2 action maps a fiber to the fiber. So therefore you get a representation from Z2 to Z2 on over a point with non-trivial isotropy. So that means over PI or a nodal point. And there's two such representations. And so we call the representation Riemann for a trivial representation. And we specify it by the number 0 inside 0, 1. So this is the image of 1. And it's known as Neveu-Schwarz for the non-trivial representation, which we will denote by 1, which is actually giving the image of 1 in this representation here. And so then now at each of our n labeled points, we get a sigma equals sigma 1 through sigma n, which lives in 0, 1 to the n. And it's going to tell us what these representations are. Another way we say this for spin structures is rather than keeping that point in there, we can remove a tiny disk. And now we have a spin structure on a surface with boundary, and the Riemann, the spin structure on that circle, on that disk now, with this Riemann condition doesn't extend to the disk, and the Neveu-Schwarz extends to the disk. Again, when I say extends to disk, I really mean remove a disk, look at that spin structure, and then that's another way one can think about these two types. Okay, and so then the rank, so we define this sigma to just equal the sum of the sigma i's, 1 to n, and then the rank of this bundle EGN is equal to 2G minus 2 plus a half n plus sigma, the modulus of sigma. So the proof is that, remember we have that, well, let me state it, it's Riemann-Roch. So actually orbifold Riemann-Roch, so I'm not going to explain that completely. I'll give a reference for it. So Riemann-Roch tells us that the dimension of H0 of theta joule minus the dimension of H1 of theta joule is equal to 1 minus G plus the degree of theta joule. And I might have to adjust this because it's actually orbifold Riemann-Roch, but let's just see how this goes for the moment. So this guy I argued is 0, and this is the rank of EGN, or the negative of that is the rank. And so then, and this guy here is equal to 1 minus G minus n on 2. And so there's actually more to this. So let me write it. So it's orbifold Riemann-Roch, and there is minus n on 2. I'm sorry, that's not correct. I'm taking the Nevers-Schwarz case. So it's minus sigma on. Minus, every time we get a Nevers-Schwarz guy, it adjusts. And so therefore, we get that dimension of H1 of theta joule is equal to, we can now see we get our 2G minus 2 plus a half n plus sigma. And so the reference here is me, and it's a new cohomology class.
Paul,
Yeah.
does this mean that both n and the model of sigma are even?
That n plus sigma needs to be even. So there's a couple of explanations of that. So what it says is that the number of Ramond boundary values has to be even. And so two proofs of that is, one is involved in actually this orbifold Riemann-Roch. You don't need to use orbifold Riemann-Roch. One can, I've told you that when you have an orbifold curve, you can just, as you've done for years, I'm sure, you can just forget the orbifold points. So when the local map Z goes to Z squared, you can just say it's a disk. And so there's this underlying coarse curve. And so then these bundles push forward, or they're sheaves actually. So these sheaves push forward to the coarse curve. And then one notices that when you have Nevers-Schwarz point, this push forward changes your degree a bit, and your Ramond doesn't. And so then you can get this from usual Riemann-Roch applied to the push forward guys. In the process of doing that, you notice that the degree of your push forward is an integer, and then that tells you that the number of Ramonds is even. I'm not giving you the detail of that degree, but that
okay,
one can do it that way. But a more common way to show that the number of Ramonds is even is a homological argument. So again, instead remove disks, and one can associate to each spin class a spin structure, a so-called quadratic form on the homology with Z2 coefficients, and then it's a homological result. The boundary is a trivial homology class, and then this calculation of what's happening with the Ramonds is a homological calculation, and this homological calculation will get you a number of Ramonds are even.
okay, thanks.
And so in particular, we notice the maximal possible rank of this class is 2G minus 2 plus n, which is a well-known number, the Euler characteristic. And that's in the Nevers-Schwarz case when all of these sigmas. equal to 1. So what we're seeing here is that mg and spin has different connected components. Sigma in, I was going to do Z2 plus, but let me just do 0, 1 to the n, such that sigma is even. I didn't have to put this condition there, it'll just mean I'm going to be dealing with empty, some of the components will be empty. So these are different connected components. And in the case, there's one extra connected component. If sigma is equal to 1 to the n, this is never Schwartz, everyone's never Schwartz, then this splits into 2, is equal to m even plus m odd, not plus, union. So there's such a thing as an odd and even spin structure, which I'm not, there's a couple of definitions of that, I'm not defining that. So in the case when there's any Ramon's present, it's connected, and but it has 2 components in the Never-Schwartz case. Okay, and now we have the forgetful map that we had a forgetful map that can forgets a point, but now a different forgetful map that forgets the spin structure. So this maps C, what was the data? P1 through Pn. Did theta come earlier? Let me put it here, I can't remember what order it was. This is going to map to C P1. So we forget the spin structure, but we also forget the orbifold structure. This is underlying, this is the coarse curve that is not orbifold. And its restriction is P sigma, we'll say is the restriction to these components. So it ends up, this defines a cohomological field theory. So we take omega gn spin. Let me actually start with my vector space and vector. So let's take H is equal to C2, which is generated by the 2 vectors E1 and E0 and E1, and it has this metric. Remember, a metric really just means a non-degenerate bilinear form, symmetric. And we get a cohomological field theory on this. So this is the push forward of the total Chern class of this bundle, this rank. Oh, yeah, this bundle restricted to its component. So this is a little bit like Gromov-Witten invariance, say. For Gromov-Witten invariance, a cohomological field theory, you push forward the fundamental class, and then the different degrees means you have different components of your moduli space of stable curves. And those different components are going to push forward to different degree terms in your cohomological field theory. Our standard example of cohomological field theory is the exponential of the sum of multiples of kappa classes, linear combination of kappa classes, and that exponential has elements in all degree. I didn't mention the trivial cohomological field theory, just the number 1, and it doesn't have elements in every degree. So this gets elements in different degree because we have all this disconnected moduli space of spin structures. And for each component, we're going to push forward and get, well, you know what the degrees are. The biggest degree is 2g minus 2 plus n, and the smallest is 2g minus 2, just that. No, plus half n, but it can't be half n, plus half n if n is even, and half n plus 1 if n is. Okay, and so this is a cohomological field theory. So I'm not going to prove that. Well, what I will say is that the proof, so I already referred to a paper by me in new cohomology classes, and one can also find this in other places regarding, look up the notion of Kyoto classes. But I'll just describe a little bit about the proof. One, just as we took the Hodge bundle and restricted, maybe I'll be doing that a bit later, so maybe I won't describe it now, but exactly we define this via a bundle, and you look at how the bundle restricts to the boundary divisors, and for holomorphic differentials, we had a good idea of how it restricts, and the same thing will be true for the square roots of the log canonical. So it's rather natural. The point is the bundles restricts naturally, and then these Chern classes restrict naturally. And then the inputs are simply just looking over different components. And so now we're going to take, from this, we're going to define something new. Oops, I've jumped ahead again in my notes. From this, I'm going to define something new, but just an intermediate guy. I'm going to define omega gn of E sigma 1 to C E sigma n to be the top degree of this. The top degree of factor. So -1 to the n, 2 to the g minus 1 plus half n plus the size of sigma. Okay, and so if you have a cohomological field theory, the top degree terms still give a cohomological field theory, because so for the kappa class that was boring. The top degree terms are in degree 3g minus 3 plus n, and any restriction of a degree 3g minus 3 plus n, oh, no, then I'm lying, that's not a cohomological field theory. It gives you 0. So, sorry, if the top degree is lower than 3g minus 3 plus n, one can see that this restriction is degree preserving, so it'll send that top degree to the top degree. So this defines a cohomological field theory, and the top degree is less than 3g minus 3 plus n. And so then from this, I want to define something new again. So I'm going to forget m points. So this pi star to the m is pi forgetting forgetting of the n points. So what I've got here, this m will always be even. If m is odd, this term is 0. So what this has said is, it says take m Ramond points, n Navier-Schwarz points, forget the n Ramond points, and push this forward. And I've said the Ramond points, really they're living in the push forward in the moduli space downstairs. What's interesting, what's really nice about this construction is due to Chirambaram, Garcia, Falda, and Giacchetto. What's interesting about this is you can't forget Ramond points upstairs. You can forget Navier-Schwarz points because the spin structure extends. So if you were to remove that point and say, oh, there's a disk there, the spin structure extends, that was fine. In the Ramond case, it doesn't. So you can't forget Ramond points. It just makes no sense to that component of the moduli space to forget that point. But when you push forward to the moduli space of curves, you're free to forget. And part of the interesting behavior of this object that I've just constructed comes from the fact that you couldn't forget it upstairs. If we'd used this and forgotten the E1s, we don't get anything interesting. We've got some just too good a structure without forgetting of the E1. And so we need this. And so the theorem from Chidambaram, Garcia-Falda, and Giacchetto is that this is a semi-simple cohomological field theory. I should say, I won't say semi-simple because it's rank 1. A rank 1 cohomological field theory, all rank cohomological field theories have to be semi-simple, and then I don't have to just define semi-simple. So it's a rank 1 cohomological field theory. It's just a collection of cohomology classes. And remember, a cohomological field theory in rank 1, we can identify the class with the image of 1. And so the proof, I won't do this in detail, given that I want to get to place in the last 20 minutes, but the proof uses the commuting of, or if somebody asks about it, I'll go through this. Uses commutativity of restriction and forgetful maps. And the fact that we're taking the top degree term. So the point is, this guy here, you would like to show that, in fact, term by term, this is going to satisfy. Oh, I should say something about this series. So, I mean, it's such an important series, and I'm about to scroll away from this screen. So, term by term, this is going to satisfy the restriction properties. But let me note that what the degree of this is. This is crucial. This could be an infinite sum. I don't want it to be an infinite sum. So the degree of this degree is equal, if you remember, it was 2g minus 2 plus, and now remember we took a half n plus sigma. So half n plus sigma, in this case, n is n plus m, and sigma, you get a 1 for every Never-Schwarz. So it's n plus half m. Probably would have been clearer to say that, and that again is showing you that the number of Ramon's has to be even. So that's the degree of this guy, but now I want to take the push forward, and so the push forward loses m degrees. Every time you push forward, you've lost 1 degree because we're going from a moduli space that's relative dimension 1. So this is minus m. So this is good. This tells us that the omega gn consists of many degree terms. The top degree term is 2g minus 2 plus n. That was when in this sum, when m is equal to 0. When m equals 1, this is an empty term. It's pushing forward a 0 class. So we go to m equals 2, and you can see now we've subtracted negative half m, so we've subtracted 1. So the next term has degree 2g minus 2 plus n minus 1, and as far down as, I guess the lowest degree term is 2g minus 2 plus, well, no, it goes on. It goes down to degree 0, of course, because this sum is an infinite sum. But the point here is we've seen that it turns into a finite sum. So there were 2 things we wanted to see. We wanted to see that omega gn has the top degree term, it's 2g minus 2 plus n, and this sum is a finite sum. So this, and then this theorem is the big idea. So in their paper, Chidambaram, Garcia-Falda, and Giacchetto, they prove that this rank 1 cohomological field theory has a certain form using a different proof than I'll present here. And they do use the classification, which we're about to discuss, but they use a so-called R matrix, translation matrix, and I'm going to be avoiding that here. But at the moment, the fact that this defines a rank 1 cohomological field theory is crucial because we have classification. And again, it really defines it because just naturality is the reason that it defines this. Okay, so. Okay, so Telemann, Giventhal Telemann maybe I'll say anyway, Telemann classified rank 1. Rank is this vector space that's involved, cohomological field theories. And so we recall that we showed that exponential of a linear combination of kappa classes, the exponential of a linear combination is a cohomological field theory, and also the exponential of the linear combination of the degree ith Chern character of this bundle that I called EGN as well, but I call it EG, so it's starting to look less like this bundle we've introduced today, is a cohomological field theory. The point being, what we looked at is we looked at the restriction of kappa m, and it was, on the G-1 n plus 2 boundary part, it was just itself, same with the lambda classes, but when you split into 2 bits, we showed it was kappa m tensor 1 plus 1 tensor kappa m, and we showed something similar for the lambda class, and but I didn't show it for the Chern characters. Actually, we're not going to use this Chern character much, but it ends up that this follows again from it. We had an exact sequence regarding the restriction of this Hodge bundle, and it's just simple properties of the Chern character. Okay, and so the classification is this is everything. Theorem due to, well, Giventhal and Telemann proved it previously. Right. Wow, I didn't know that was possible. I'm not used to this software on this computer. I'll try to turn that off. Right. I'm away at the moment from home, and there's some different software on my. Okay, so this is all. So if you have a rank 1 cohomological field theory, this is what you are. So what does this mean in our case, corollary to, maybe I won't say corollary because there's 2 theorems in play. So I'm not going to, I'm going to say that we have this, this object, omega gn, which was this big sum of push forwards, and we now know that it's equal to this. Okay, so now let me just, I don't want to recall what omega gn is, so I think I can maybe. I'll just move really quickly. So remember, this omega gn is this sum where we push forward all of these classes. So we've constructed some classes on the moduli space of curves, and we're going to find our k polynomials are coming out. And the point is, we know something, that we have structure of these classes, which I will mention soon. But at the moment, I want to see these. So I should just repeat. This construction of this omega gn may look ugly, but it ends up, we have some properties, some really nice properties that I haven't proven to you yet. And now, using this classification, we've said this omega gn consists of kappa. This exponential turns into just polynomials in kappa and classes and Chern character degree m Chern character guys. And so what we're going to do is show there's no Chern character guys. So we're going to see these omega gns going to give actually the kappa polynomials. And the point is that we have some nice properties of the omega gns, and it's going to satisfy the property of the final theorem I stated yesterday without proof. It's a really elementary proof. But anyway, let's go forward here. So this is the kappa I. So what this says is we now just need to calculate these values. And so Maxim Kazarian was asking why these coefficients AI.
Paul, and what are mu i's here?
Oh yeah,
What?
yeah, that's just from my notes. Okay, so let's calculate the AI. So it ends up that pi star of gamma g n plus 1. This is one property that I didn't. I'll prove it now. Okay, so
one question. Sorry, would you explain what is this the meaning of this classify in rank 1?
Oh,
before even going.
The meaning of it is this. So it ends up that what we've shown is that this gives an example of a rank 1 cohomological field theory. Choose any A's and B's, and you get an example. The theorem is if you are a rank 1 cohomological field theory, you must be of this form. There are no others. So classification in this case means, hey, can you tell me about all cohomological field theories? And the answer is, why, yes. You just need to find numbers A and B.
And if we are not able to write it in this form, so it's not a rank 1.
Well, but this is exactly what's happening here. We, oh, maybe I misunderstood. This gamma GN has been delivered to us not in this form, so we're now going to try and find them like this. But if you're a cohomological field theory, just these nice restriction properties, this is actually a deep theorem, forces you to look like this. Is that okay?
Yeah, and it's two way. So if we are able to write it in this way, is rank 1, and if it's rank 1, it's always like that. So it's two-sided.
Yeah.
Okay, thank you.
And I may have written in one set of my notes, I used 2m instead of m. So indeed, I think this is just should be an m here. Okay, so where does this come from? So I promised that we're going to have something looking like, so it ends up that we have this sequence over, now we're back upstairs, MGN spin. We have that, we still have these, the same line bundles that give a cotangent line at these points. There's something orbifold about them. So there's a factor of a half that gets introduced, but it's the same line bundles, the cotangent bundle at orbifold points. So it's fine. And then there was this bundle that we constructed. And then we have this pullback. So here's the statement. Recall we did this for the Hodge bundle. By the way, I won't use this terminology again. I don't like these boxes. It looks like I'm doing some type of partitions or something like that. I realize how much it looks like that. Okay, so so we did this with the Hodge bundle. We said, well, actually, with the Hodge bundle, this is trivial. The pullback, we did this for the restriction of the classes. So it ends up that the restriction of this bundle to boundaries is what makes it a cohomological field theory. But now the pullback has a nice property, and this is the pullback. And so what that tells us, let me just cut to the chase, is that the total Chern class is equal to this, and where psi n plus 1, I've told you this is a technical detail what I'm putting there, I'll put it in brackets. The psi n plus 1 down on the moduli space of curves, it's the same one upstairs, there's some factor of half due to the orbifold. this now tells us that if I was to push forward the top degree term, the push forward of this the top degree class, or maybe I'll spell it out. No, I won't because of the time. So the push forward of this top degree class now is introducing a 2g minus 2 plus m. That's just the, and it's not a psi n plus, well, it ends up as a psi n plus m plus 1 that we'll apply this to. And when you push forward this, I've said something incorrect here. Sorry. I'm concerned that lives somewhere else more significant, that error. It didn't make sense what I was saying. I can't compare those term classes. But now I can, and so now when you push forward this left-hand side, let's push forward to the right-hand side, and that introduces an Euler characteristic, and that's what this 2g minus 2 plus n plus m is. Okay, and then what that gives us is the AIs. Therefore, the AIs. And so this was Maxim Kazarin's question. Why are these particular, so therefore AI is equal to SI. And why is that? So, well, if I take the push forward of this exponential, so remember I've used the construction of these gammas, this bundle, this exact sequence to get this property, but I can't see this property in terms of the exponentials. It actually is a strong statement of the exponentials. If I take the push forward of x sum AI ki plus bi, term what I sometimes write an EGN, well, this is equal to, remember the trick, we take this as the pullback of ki plus psi n plus 1 to the I, plus these guys are already satisfied. They're already the pullback. They don't care about marked points. And so then everyone's a pullback here. When you push forward, this is a ring homomorphism, you're left with exactly this same expression, some AI kappa I plus times the push forward of the exponential of some, there's an exponential missing. The exponential of some AI psi n plus. And so, and this is equal to 2g minus 2 plus n times this exponential of this by this line above, 2g minus n plus n. And so from this, the first of all, I'm not now going through each detail because of time. And sorry about that, it's got messy, hasn't it? But the churn character is irrelevant to this because it's in both factors, all right? So the churn character doesn't come up, nor for the exponential. So the exponential doesn't come up. And so what we get is we get I'm not explaining this well, but this is just about polynomials. These psi classes, we don't really care that they're psi classes. So let me say that this uniquely determines the AIs. To have this property, this push forward property, the only thing I want you to get from this proof, which I haven't spelled out in detail, is that the BIs are irrelevant to this property, this push forward property, and the AIs are uniquely determined. So intuitively, you can probably imagine that, because if you expand this in a power series, you'd notice that each of the AIs is little by little being determined by the smaller ones. So let me not say more. And then the BIs come from the calculation on one end. So one can calculate these guys, and this is enough to find that the BIs are equal to 0. So I'm not calculating them today, okay? And so then what that tells us is that gamma GN is equal to K, and we also use this property that the gamma gn is, sorry, yeah, gamma gn is, this is this k polynomial, right? This is k0 plus k1 plus k2, etc. And then the degree 2g minus, so it ends up that gamma of the top degree of this is what's defined to be a theta class that I introduced, didn't introduce, I just named it. And so what we've got here, this satisfies, this has been proven to satisfy a property in again, the paper that I cited already, that this is given by the product of the size classes times the pullback of theta g. And so we now have that this is true of the k2g minus 2 plus n, and I didn't give the proof. Sorry, these are just straight k's, I guess. So that proof, I might just sketch it because I can take a couple of minutes, I think. So the km is equal to 0 for m greater than 2g minus 2 plus n, and gn not equal to where it's not the case, it's not the 3g minus 3 when n is equal to 0. So mn is not equal to 3g minus 3. So this nice trick, of course, we've tried to implement this for the J polynomials, and I believe it will work. It's just that what did we do here? We came up with this spin moduli space and produced some cohomological field theory just from somewhere, and then we proved these properties. So similarly, we need to produce a cohomological field theory from somewhere for the J polynomial, so we have candidates for that. So let me just sketch this, the proof that was supposed to appear in last lecture, because it's elementary, and that is the proof of this. Proof of this implication. So here's our assumption, and here's our proof. So what we do is we're going to use all of our nice properties of these classes, but we're going to take a very special graph. So we take k and n both greater than 0, and we take this stable graph, which looks like this. So there's, and these are all genus 0. Remember, I'll remind us what our stable graph is saying. So each vertex is giving us an irreducible component. So maybe I'll draw the picture as well, and there's n of these, or n minus 1 of these. So this corresponds to a curve that looks like this has genus G. It has n minus 1, well, actually n points, because there's a nodal point here. And then there's just these genus 0 components, where this has 2 points and each of these only has 1, because they've actually got 3. They've got 2 nodal points in that. So that's the curve that we're interested in, or we're actually interested in this whole substratum, m gamma bar, which is mgn bar cross m03 k times. There's k of these. And this maps gives you an, it's no longer a divisor, it's a codimension k, just the number of edges. interior edges, codimension K subvariety of mg bar n plus K. Okay, and so then if I take the restriction of this class, K 2G minus 2 plus N plus K, I get take K 2G minus N plus K tensor 1 in all these factors. So let me describe both of these equalities. So this uses this equality here uses the fact that K 2G minus N plus K is equal to the product from I equals 1 to N plus K psi I times pi star K 2G minus 2. So there's a psi I which vanishes on the corresponding factor of M03. So, therefore there exists, maybe I'll put this below, therefore there exists a psi I on my, let's call this I here, a psi I restricted to M03, where there's two unlabeled points, but there's a labeled point with the I, and that's 0, just because the psi class is too big. It's a degree 1 class or a chronological degree 2 class on a 0-dimensional moduli space. So what this says is that this, because we know about this factorization, it says that when we restrict it to this, it just vanishes just because the psi class annihilated those. So that's that equality. And then the second one uses the degree 2G minus 2 plus N plus K part of this. Recall that we have, this is what we spent the first couple of lectures hopefully getting familiar with, that when we restrict this, we get, I'm going to go over the edge, I think. We get that this restricts, oops, I hope something upstairs that's valuable didn't get taken away. It was the tensor product that got taken away. This is tensor. So this is just iterating this restriction. And this is an element of mg n bar, the cohomology, and this lives inside the cohomology of mz03 bar tensor k. But we know the exponential in this degree, in this dimension 0 guy, that's equal to 1. Right? This is equal to 1 tensor, well, maybe I'll do it this way. So 1 tensor k, which lives in, it's the only class that can live in this. I hope do I lose my big line? If I just touch that. I don't need it, I guess. So what happens? Gone. My other software would only erase the local bit. Okay, and so then, so what we have here is that the pullback of K2G minus 2 plus N plus K is still K2G minus N plus K just in this component. And we've got 0 is equal to that. And so that is what we need. So what we've said there is Km equals 0 for M greater than 2G minus 2 plus N, and N is greater than 0. And then we didn't do the N equals 0 case, but that uses our push forward case. So N equals 0, we push forward the N equals 1 case. We've also got to see this one case that doesn't work. And what we find is that Km is 1 on 6G. Remember, we had a nice push forward for these K polynomials. The push forward of K is a multiple Km. And now we know that kn plus 1 is 0 because we just proved it when n is, this is in mg 1 bar, and this is in cohomology, of course. And this is in mg bar, cohomology. And so then this is equal to 0 as long as for m not equal to 3g minus 3. So we can see exactly the failure of this argument, and indeed we can check that it doesn't vanish. In fact, the integral over mg bar of k 3g minus 3 is not equal to 0. We can calculate it explicitly. And so this argument breaks down, and in fact, it's not true, the result. Okay, now I went further over time than I planned, but that's, I'll finish there.
Okay, thank you, Paul. Are there any questions, comments? It seems no. All the questions were asked during the talk. Let's thank Paul. Now we have a lecture course. Yes, Netla, what kind of link do you want?